Hello, hello, hello. All right, let's make sure I've got stuff going on. All right, can anyone hear me?
Yes. I don't know if you needed confirmation, but there you go.
That's very helpful. Thank you. I did. That sounds like a very feminine Paul. Something changed.
No, that's Sam.
I figured as much. Awesome. Okay, so this is obviously the first time I've ever done this. So this is as much a test run as anything for today. Really, there's not a whole bunch to talk about today other than the midterm, if anyone wants to go over that or talk about any of the questions on that. And also the plan for the rest of the semester. Because, I don't know, the idea of sticking to a rigid kind of class schedule doesn't seem to make as much sense now as it did a few weeks ago. So, does anyone want to, let me just dig out the, oh crap, where's that gone? Here we go. Anyone want to go through the midterm? Hang on, there's chat down here. What's that mean? Oh, yeah, that's Sam. Okay, stop that. Bloody hell. Oh, hello, Louise. Okay, cool. All right, so, all right. I'm keeping an eye on chat on the right as well, so you can send chats there. Some you can do them privately. You can do it to everyone as well, also. So hi to everyone again. One of the questions was, how will we be getting the midterm back? And the answer is, I don't know, to be honest. I have them all on my desk in a nice pile, but obviously that's not great help because I can't get them back to you. So next time I'm in, I'll I can probably scan them actually. So yeah, I'm just trying to think. There's a lot of things to scan and send. I'll scan them and then email them to you separately. Will be the solution to that, and then you can compare that to the exam posted on Blackboard. I think would be the best solution. You're probably very happy to know that only one person got the Carl Sagan question wrong, which was, I thought was kind of neat. Anyway, so let's see if I can do this right. So I'm going to try. See if I can share screen. Haha. Okay, I got the midterm. Let's get rid of that. Here we go. Okay, so yeah, the midterm was, I don't know, I guess to be honest, I was a little surprised because I thought that based on the quizzes, most people were pretty much getting the stuff, but I think the issue is the difference between the quiz format and the multiple choice only exam format, which is a little bit less forgiving, I think. And also because of the way that multiple choice works, yeah, kind of lends to being more specific, I guess, because hey Robertson,
Hey, how are you?
very good. Yeah, because you have to give the answers, it kind of lends to being a more specific type of question. So I think that may be one of the ways in which people are caught out a little bit, because you have to be very precise. Obviously, there's only one correct answer. So some of the questions are obviously harder than others. So there's a fair amount of basic recall here, which is kind of inevitable for both a multiple choice and this kind of class. There's just a lot of stuff you need to know to put everything together. So the first question, people typically answered this one: bilaterally symmetrical organisms. So when I was saying about you need to know what order things occurred in, essentially, this was one of the questions that addressed that. So these two, can everybody see me working through the document online on the screen? Let's see, where's chat? Oh, ouch. Hang on, I'm trying to get.
Yes.
Thank you, Robert. Cool. Yeah, I'm just trying to figure out how to work this bloody thing, to be honest. All right, let's stick that over there so I can still see that. All right, so yeah, these two answers were beforehand, essentially, right? So obviously photosynthetic plants came way earlier. Multicellular animals, likewise. Jawed fish were much more complex. They were afterwards. And so the two choices really were between bilaterally symmetrical organisms and chordates. And so one of the really big things about Cambrian era fauna is that they were really the predecessors of everything that we have now. Ediacarans, which were the bilaterally symmetrical organisms, are not. And so the big deal is having a notochord, being chordates. And so that was the answer to that one. This was the correct answer. And so that's where knowing kind of essentially what happens and in what order makes a big difference. Hey, one thing that I'd request for people that are signed in is please mute your audio unless you want to say something. And so the reason for that is that I don't get feedback, or if your cat happens to run in and scare the crap out of you, it's not going to affect everybody else. Okay, so 2, very simple. It's middle of the sequence. The main sequence is really size and brightness from very large and very bright to very small and very dim. And we're kind of in the middle. So that was just a fairly simple question. Just make sure. This one was, again, sorry. Hopefully no one answered creationism, because that's not the best way of thinking about this. It's uniformitarianism, right? So the idea that we can apply what's happening now to what's happening a long time ago, because they're going to be the same processes, right? And so if that didn't apply, then all that stuff that we find in really old rocks, it's irrelevant, essentially, right? And so this is the theory by which we can compare things now to things that are very, very old. Okay, so this one's, because I'm at the moment kind of going through a lot of the material for the rest of the semester, right? So I've got a bunch of different lectures that I need to record. I'm going to start this afternoon, basically, or right after this. This is a really important thing to get for a lot of these, how do I put it? A lot of the molecular characteristics, a lot of the biochemistry and cell biology is going to be really important to understand, because it's the basis of all of these adaptations to extreme environments, right? So when we talk about barophiles, piezophiles, hang on, that's the same thing, psychrophiles, halophiles, thermophiles, all these different kinds of things, right? We're going to be actually referring back to properties of those macromolecules and molecular cell biology, right? So it's really important that you get this stuff. Otherwise, that extremophile biology is like, you know, it's just not going to make any sense. It's just going to be a list of stuff. So phospholipids are actually, they're defined by 3 properties. Their head group, which we didn't really talk much about because it doesn't affect much of the things that we're interested in. Their fatty acid tail length, because the longer they are, the more ordered and more rigid the membrane, and the degree of saturation of the fatty acid tails, where more saturated equals more rigid at a certain temperature, right? So the answer to this one was essentially these 2, right? Which is E. Okay. 5. This is again, a kind of a recall question, but you can also work it out from first principles too. And this tells you that it is an autotroph, right? Because it's getting its carbon from an inorganic gas, right? Essentially, I'm not sure if CO2 no, it doesn't count as an organic molecule. I don't think so. Anyway, so if it uses CO2 as an autotroph, right? So you can basically get rid of A and D. We're A, basically, organoheterotrophs. And then hydrogen gas tells you it's not a plant, right? Because plants don't use hydrogen gases, they use light. It's not this one. I struggle to think of examples. I think methane oxidizers are probably the few that fit in that one. It's a chemoautotroph, right? Because it uses a chemical as its electron donor, and it uses CO2 as its carbon source. And we'll be looking at a lot of those over the next few weeks. Okay. Bit of a mix of biochemistry and astronomy in question 6. Fairly simple question. It's just something you need to know. But we did talk about this a fair bunch, and that's the L enantiomer. For amino acids is preferentially, actually it's almost, I think it's entirely used. Our enzymes don't recognize the D enantiomer. But interestingly, sugars are D enantiomers, not L. That's just kind of like a fun fact. Doop-a-doo. Okay, so question 7. And so hopefully as you get it, a lot of these questions are really geared to not just test your knowledge of what we've already done, but also to kind of lead into, future stuff. And this is one of those. Actually, the 8 is as well. And so this is all about when Earth turned into a giant snowball, we think, completely covered in ice. And so essentially the cause for that was decreasing temperatures. I'm not entirely sure why temperatures started decreasing in the first place. It's possible that it was because of CO2 concentrations decreasing. But what it essentially led to was a feedback effect with albedo. And so as the Earth cooled, the polar ice caps expanded, right? Kind of, a glaciation event, basically. And as the polar ice caps expanded and albedo increased, right? Because ice is far more reflective than water or forest or anything, or savanna or whatever. More light was reflected back into space. Less thermal energy was retained in the atmosphere, and so the Earth cooled again, and those polar ice caps expanded a little bit further, and so on and so forth. It's basically a positive feedback loop. And so question D was the one there, right? So hopefully you can see that like how my mind works when it comes to exams. right? There's a bunch of stuff that you just need to know. They're just basic recall questions, right? Just, what's a halophile, right? So an organism like salt, or lives in high salt concentrations, for example, just basic recall questions. And then there's other questions where you need to actually think, okay, what's the process? How do these things work? What's the principle? And question 7 is very much, well, actually question 8 as well, is an example of that, right? Question 8 is actually a little bit more kind of a mix of the two. But question 7 is definitely one you have to work out. There's also another one further down on half-life, right, where you have to really understand what's going on to be able to work out the correct answer. Anyway, so bless you. Robertson, do me a favor and mute your audio, would you, unless you need to ask a question?
Okay, no problem.
Thanks. I can tell that you're sneezing because I can see you, so I can still say bless you if needed. All right. Io, it's the innermost Galilean moon of Jupiter. And so we talked a bunch about how it's a very weird place, right? And its weirdness is partly because of its location. And so it's a long way from the sun. So Jupiter is, what is it? 10 astronomical units from the sun, so 10 times as far from the sun as we are. So it doesn't get a lot of light or thermal energy from the sun. And it's not a high mass because it's, I don't know, well, relative, similar to the moon, I think, maybe a little bit larger. But it is in a very strange orbital resonance with the other Galilean moons. Sorry, blocked nose. So essentially, Jupiter, massive, and then ding, 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 4 Galilean moons. And they're all in resonance. So essentially the outermost one, which is Callisto, goes around really slowly. That does 1 revolution, right? Inward, closer to Jupiter than it, is Ganymede, which does essentially 2 orbits for every orbit that Callisto does. So Callisto is doing this, Ganymede is doing this. Then you have Europa, which is further in again. That again doubles the number of orbits. So it's doing 1, 2 for every 1 that Ganymede is doing, 1, which is basically half of what Callisto's doing, right? And Io's in again. So it's the same deal. So essentially you have one doing, 1 orbit, and then the next one is doing 2 orbits, the next one's doing 4 orbits, and the Io is doing like this, is doing 8 orbits, right? And so that means that at different points around Io's rotation around Jupiter, it's obviously getting pulled by Jupiter because it's massive, but it's also, oh yeah, that's right. Thank you, Angela. Io is one of the Galilean moons of Jupiter. That's right. So it's being pulled by, Jupiter. So it's like getting pulled like that. And it's kind of hard to do it with a hand, right? But it's being kind of pulled in a kind of egg shape towards Jupiter, right? Because of its massive gravity. And then when all of the other planets align, they're kind of tugging it backwards, right? So their gravity combined basically pulls it a little bit more round. I'm talking about Io right now. And then those other planet, Io zips past them and it goes back. And so basically it's just doing this as it goes around Jupiter. And because it's doing that, it's like a tennis ball, right? If you have the, hand strength to squeeze a tennis ball for a long time, it will get warm, right? And that's essentially what's going on with Io. And that's really important for when we look at Europa, because Europa isn't as hot as Io, but it's hot enough to have liquid oceans, under the surface of its ice. And so it's a really, really important place for astrobiology. Okay, quick question 9. Hopefully, well, all bar one of you did get this. It's Carl Sagan. The only person that didn't get it thought it was Karl Marx. And he's a very important guy for a lot of reasons, but not for astrophysics. Igneous rock is from lava, right, which is essentially magma that comes. Oh, sorry, question 8. Good point. Thank you, Robertin. Tidal flexing. So this one. That's what that kind of squeezing is called, right? Because essentially it's like the tides on Earth are caused in large part by the moon, right? And so that's why that tidal part comes from. And flexing is because it's just doing this. Okay. Right. So anyway, question 9, Carl Sagan, obviously. Question 10 is magma. The other ones are shellfish, sedimentary rock, sedimentary rock, sedimentary rock, meteorites. Yeah, I mean, that's just all kinds of weird stuff that falls out of the sky. Mostly those are either rocky or metallic. Here's another basic recall question. You should also get this from your chemistry as well, right? This really isn't anything that you shouldn't already know from elsewhere. And the difference between these two isotopes is their neutrons, how many neutrons they have. C12 has 6, C13 has 7, right? So it changes the mass of the atom, doesn't change the charge. Okay, let me just have a, I'm going to speed up a wee bit because I've only got 40 minutes on this. Unfortunately, I can't do the whole 50-minute lecture just because Zoom has a limit for the free version, essentially. Okay, so question 12. This was very much a question about Carl Sagan's work when he had it's a Galileo probe turn around and look at the Earth. Right, so if you have a lot of oxygen, and let me just type it down here so I can, I'm not going to try and do this. Hang on. Essentially, if you have methane and oxygen, you're always going to get CO2 and water, right? Always. It's I mean, obviously it takes time, right? But that's the most thermodynamically favorable outcome. So if you have a lot of oxygen, right, you're not going to have a lot of methane. You're not going to have any methane, actually, if it's all that methane is produced inorganically, right, through, I don't know, eruptions or whatever, right? So if there's a lot of O2 around, like there is on Earth, you would not expect to see any methane because it'll all be converted into carbon dioxide and water. Oh, cool. Don't have a time limit anymore. That's nice to know. And so the answer here, let me just get this back out of the way, is none. Right, because the only way you get more than none is if this was wrong, if there was life, right? Something that was continually producing methane in sufficient quantities to overcome that thermodynamically favorable outcome, right? Pardon me. Oh, okay. All right, so this is a getting slightly more comfortable position. This is a one of those thinking questions, right? And so essentially, one thing that you need to know is that the half-life of any radioisotope is the amount of time it takes for that radioisotope to decrease by half. It could be its radioactivity, it could be the time it takes for it to convert from one thing into another, which is essentially the same thing, right? It just depends on how you want to think about it. So if you have half the amount of that radioisotope around, then the amount of time equals to its half-life has passed, right? So in the case of C14, that would be 5,730 years, right? If you're looking at a sample that had half the amount of C14 as it would have now. So if it had a quarter, essentially it's a half, of a half, right? So it's going to be 2 half-lives. And so 2 half-lives is simply 2 times that number, right? And so the answer there is 11,460 years. If it was 1/8 of the amount, it would be 3 half-lives, so it would be 3 times the half-life. If it was a 16th, it would be 4, so it kind of goes on and on. It's an exponential decay curve, right? And so that's really the basis of radiocarbon or even any radioisotope dating, right? Is there's a simple calculation based on how much you have left, right? If you have like E amount, then it's however many half-lives it takes to get to that tiny amount is how old it is, right? So essentially it's turning it around from kind of how we thought about it in class. 14, oh, right. Yeah, so the half-life, so the time is invariant, right? The thing that changes is the amount of radioactivity. So that's where it's a little bit trippy to think about, right? So the time taken for that process to happen, for half of it to decay, is always the same. It's really, really, really fixed. Astonishingly so, actually. And so the amount of time, for a certain amount of radioactivity doesn't change, but the amount of radioactivity does change. So yeah, it's kind of take an idea, flip it around again, is very much the case for this. Hopefully that makes a little bit more sense. 14, this is just straight up recall, it's lead, right? 15, oh, did I not send that? Crap sticks, sorry, I'm trying to figure out how to use this bloody thing. Yeah, that was for a previous question. Let's see, yeah, I'll get used to this, promise. Okay, so number 15, this is about, let me just get my jumper off for a second. That's better. This is really about the properties of different, well, it is gas giants. So what is a gas? Equation for 13. Oh, sure. Hang on, give me a sec. I'll remember to try and send this time. So, how would I write that out? Just thinking. Amount of time equals, what would that be? Inverse of Chiara, I will save it. Thank you for the reminder. The recording will be saved. I'm not sure if the chat is automatically saved as part of that, but I'll save it separately. Amount of time equals inverse of amount of radionuclide, if I can spell that, times half-life. Is that right? That's not very good. That's not 100% right. I can't spell radionuclide. So, well, actually, probably a better one would be amount of time. Number of half-lives used or passed times half-life time. There you go. There you go. That's kind of as good as I can get it. Where are we at again? All right, so let's see if I can stretch this down a little bit. Yeah, so it is about gas giants, very much so. So that's what if you think about a gas, right? So if you take a camping stove of propane or whatever it is in there, and you're a bit of a local yokel and you shoot it with a gun, right? If a bullet goes through, most likely it'll explode, right? Because it's a volatile compound, right? It wants to react. It wants to kind of disappear, right? It doesn't take very much to get that compound or atom or whatever to either react with something or to get blown away, right? To be given enough energy to disappear. And if you think about, okay, well, what happens if you shoot a rock? Nothing. It just stays a rock. Most likely the bullet wangs off somewhere and, disappears. So that's exactly why those gas giants are there, right? Because all of the gas, right? So, there's probably a ton of hydrogen gas that was, forming in the inner solar system that, now consists of like Earth and Mars and the like. You don't find hydrogen gas here, right? Outside of, sealed pressurized containers. And the reason is it just disappears, right? It's so volatile, it will just go into the atmosphere and basically it'll be lost, right? And it's the same with, water, for example. We've got, frozen ice at our poles. There's no frozen ice on Venus, and there's nothing very much on Mercury, actually, other than just rock, right? Rock and metal. Mars, there's a little bit more frozen stuff. They've got frozen carbon dioxide, right? And so you can see as the further you get out from the sun, the less thermal energy there is there. So things that would normally be that would escape or react or get blown away literally from that planet hang around. And so that's why you have really rocky gas, right? And then after those gas giants, then you have slush balls, right? And so essentially the further out you get, the more solid things are going to be that would be volatile or gases further in. And so the answer to 15 is volatile, right? All the other ones basically mean rocky or metallic, right? And so if you just think about the different you're welcome. Yeah, don't shoot volatile gas containers. It's just not a good idea, generally speaking, unless you're, fighting off a giant white shark and you're on a boat and, stuff like that. Anyway, hopefully that answered that question. 16, this is a virial theorem, right? So essentially half of energy is retained, half of it is radiated away, right? And the half of it being radiated away is still happening. That's why the Earth is warm, essentially. Or one of the reasons at least. Yeah, don't go finding giant white sharks. I actually watched a film called 47 Meters Below or something recently. That was also, again, about people being eaten by giant white sharks. They're actually not that vicious. They have a terrible reputation. Yes, I know. So a question, statement from Chiara in capitals as well. Yeah, that totally screwed up the whole Shark Week. Give me a second, Robertson. We're on a tangent. So I don't know when I'll be able to do Shark Week. What I might try and do is next time I'm at work, which will be later this week, I'll try and find Dr. Shelton and get the shark costume. So at least I can wear the shark costume while I'm doing these sessions. Not sure how these will fit around the shark costume, but yeah, I don't have it yet. I'll do my best, right? These are difficult times. Anyway, question 16, Robertson. That is C, half of it. Oh, Dr. Sheldon doesn't have it? I thought he said he did. Talking about shark costume now. You're welcome, Robertson. It's not, yeah, okay, so two things going on right now. So I'm looking at the chat annals and different things. Shark costume, I'll try and find it and get it, and I'll wear it, right? I solemnly swear. Back to, well, okay, I've got to move on from the shark costume. Otherwise, we're just going to get like totally distracted there. I've got lots of ideas. It's going to be fabulous. All right, so don't worry about that. Rotation, no. So the rotation of a planet or moon is essentially due to the original rotation of the protoplanetary disk, right? As far as I'm aware, and its interaction with other things around it, right? In terms of moons. So some of it is, oh, actually, no, you're right. Half, I'm just trying to remember back. Half of it's radiated away as heat. The other half is converted into its angular rotation. Right, there you go. Thank you, Angela, for the reminder. Okay, back to, that's good knowledge. Okay, another question for extremophiles, right? Kind of prep question in a sense. So the idea here, and we'll get to this again when we talk about barophiles or piezophiles, right? Organisms at high pressure, because essentially cold and high pressure are the opposite to high temperature, right? They're at the other ends of the extreme essentially. And so the idea is that proteins have to move to function, right? They kind of flex or kind of rotate or, you know, whatever, right, to do their job. And to do that, they need to be able to both be mobile, essentially, yeah, they need to be mobile enough to move, but not so mobile they'll just fall apart, right? And not kind of like locked together, right? And so it's a very delicate balance, and it's very much specific to that particular temperature and pressure context. And hypothermophiles live at very high temperatures. And so if you put a lot of thermal energy into something, it's going to make it kind of vibrate. And our proteins, or egg protein, so if you put one of us on a skittle, or skittle? No, skillet, there you go, or an egg, right? Essentially what happens is all that thermal energy makes those proteins kind of denature, right? That's the technical word for it. Change shape. That's why an egg goes from translucent to being solid white, because the albumin, which is a protein in it, loses its original shape and then kind of folds back into some other funky shape, which is not translucent. Anyway, so to keep those proteins in the right kind of format, right? The more energy you put into them, the stronger the bonds you're going to have to keep that protein in its correct shape. and still be able to move, right? And so at the highest temperatures, you're going to need more of the strongest bonds. And I even put them in the order for you, which I thought was rather nice. And so the answer is disulfide bonds, right? Covalent bonds. Those are the only ones that have enough strength to hold those proteins together with all of the energy that's getting pumped into them from the environment. So that's why disulfide bond is the answer. And vice versa, in very, very cold environments, right? You'd expect to find very few disulfide bonds. Oh, let's move that up so I got my eye on the time. Whew. Time is moving fast. All right, question 18. Methanogens make methane, right? That's what they do. Usually, yeah, sorry. Like to break down the word, right? I like kind of figuring out how words are made, essentially. So, let's see if I can do this. That bit, methane. That bit, maker. That's what gen means at the end of something. Just how those words work, right? So you can just know that, right? So if you know that, then obviously that's the right answer, right? So they use CO2 to make methane. The other way you could figure that out is you can't reduce. So you might have thought it was this one, right? Can you reduce methane to carbon dioxide? No, because carbon dioxide is more oxidized than methane, right? That's why plants use it to reduce it into glucose, right? And we oxidize glucose into carbon dioxide, right? So there's two ways you could answer that question. One, just by knowing it from the word. The other one by figuring it out again from first principles, right? The only way you can't get question B, it doesn't work, right? Because you can't reduce methane to carbon dioxide. You're welcome. So question 19, Ceres is, or Ceres, not entirely sure how it's pronounced. It's a very large, what's called a planetesimal in the asteroid belt. And so because it's in the asteroid belt, it is round and it is differentiated, right? So it has a lot of the trappings of being a planet. It's pretty small, right? So it's smaller than the moon. But, you know, Mercury is kind of pretty tiny too. But it doesn't own its own orbit, right? Because it's in the asteroid belt. There's a whole shit ton of other stuff in there, right? So it's not a planet. Even though if all that other stuff wasn't there, it would probably be called a planet. It would just be a really, really, really small one. So it's not the A-team answer, number C, it's number D. Hopefully there's someone old enough in the audience to get that joke. Question, yeah, that's right. Question 20, BIFs. So banded iron formations, the iron is iron that's precipitated out of solution, which is oxidized iron. It's rust, basically. And the only way you get rust is with oxygen. Pardon me. So the answer to that one is question A. Luca, all of the above, right? All of those things apply. Again, when you're looking at these types of questions, your very first task is to see if two of those answers are right. And if they are, question E must be right. Answer E must be right. That's basically the way to do those all of the above type questions. Coacervates or coacervates, I'm still not sure how to pronounce that, are basically structures that emerge out of solution which are distinct from that solution, right? And the easiest ones to think about are mycels and vesicles forming from phospholipids and stuff like that. Amino acids can also form classavates as well, but the easiest one to think about is lipids. And so that really plays into this answer. So it's all about compartments. Basically, being distinct from your environment is really what classavates are all about. Funky word. It is a word of the day, actually, I think, for one of the lectures. 23, red dwarfs. We're going to be seeing a lot of red dwarfs, right? They are fairly well overrepresented in terms of exoplanet formation. And there's a lot of different reasons for that, which we'll talk about later on in the course. But they have particular properties. They're small, very small. That's why they're called dwarfs, right? You don't have large dwarfs. They're red because they're on the very end of the main sequence, right? One end is super bright white stars like Pollux, I think, Betelgeuse are good examples. We're in the middle, red dwarfs at the end, just before brown dwarfs, which aren't actually stars at all, right? And so they're short, small, live forever, not very hot. Their output, UV output, is variable, right? It's actually very highly variable. So even though D looks like it kind of might be right, it's not. What's the word of the day today? Procrastination. That's what the word of the day is today. Thank you, Paul. Yeah, I'll even type that for you. Anyway, I'm not going to procrastinate anymore. I'm going to get off my ass. Oh, actually, I'm not going to get off the ass because I'm going to. Can I use in a sentence, please? My spring break has been an exercise in procrastination. There you go. Does that work, Vivian? Basically putting off stuff that I should do to do other things that I want to do, which, you know, is kind of human nature, I guess. Anyway, back to the question. So the cool thing about red dwarfs is because they're so much cooler, their habitable zone, which is where you're likely to find liquid water, is a lot closer in. In fact, for some of them, yes, it's a very pretty smile. Thank you, Robertin. Some of them, the habitable zone actually extends inside the star, right? So our habitable zone is basically kind of between Venus and Earth and Mars, right? That's our habitable zone, and we're in it by definition. Red dwarfs, that habitable zone can extend all the way to the star, right? So obviously you're going to have a lot more potential sites for life to emerge if there are a series of, you know, planets within that habitable zone. Question 24. Water is the answer. Other things may be potential signs of life, but the main thing that's required for life, at least as far as we know, is water. That's question 24. 25, the higher the mass of the star, the shorter its life, the brighter it is, the whiter it is, right? The higher its color temperature. Got nothing really to do with rotation speed or number of planets, as far as I'm aware, at least. Question 26, Pluto and Charon, they are tidally locked to each other. So they rotate like this, right? I'm trying to do it now, right? So if this is the moon, this is the Earth, right? The moon always rotates with its same face to the Earth, but we don't rotate with the same face to the moon. That's the case with Charon and Pluto. They always show the same face to each other. So that is D. Question 27, right? So the most of the rest of the mass of the solar system are Jupiter and Saturn, the gas giants. So that's answer is D. So that's just something to know. You might have thought sea, maybe. It's quite a misconception to think that inner rocky planets, even though they're rocky, they're very small, right? And so mass is a function of both size and density. And Jupiter is huge. It is like you could put Earth in there like hundreds of times over, essentially. Okay, 28. Again, another question on that. What's answer question number 23? 23. E. It's because their habitable zones, you're welcome, are larger and closer. Where we are. Do. All right, question 28. We're looking for chemical disequilibria, right? So that's presence of both oxygen and methane, which you wouldn't expect if life was not present. We're looking for the red cliff, right, which is a sign of photosynthesis. And the other thing, which is actually what a whole bunch of people have been looking for a long time, is radio wave transmissions, right? Because that's not just a sign of life, but it's a sign of life that's able to put together a radio transmitter, right? So presumably intelligent life, right? That's what Galileo was looking for, and it found it too. Question 29. Some people got mixed up between differentiation and stratigraphy, right? So stratigraphy is the layer in which sedimentary rocks form, and they form in terms of the one at the bottom is the oldest, the one on top is the newest. That's not the same as differentiation, right? Stratigraphy really applies to like the lithosphere, the crust, the very topmost part of our planet. Differentiation applies to all planets, and it's really about the heavy stuff going in and the light stuff staying on the outside, right? So if you think about gas giants, for example, right? They're gas, right? So there's like all this gas on the outside, that's light stuff. In the middle is the heavy stuff, whatever that might be, we have no idea. Molecular hydrogen, metallic hydrogen, I don't know. That's what differentiation is all about. Oh, and question 30, right? So this was we spent a bunch of time on these two papers, and the reason was because they're super cool and they're also really, really interesting as well. And there are two different papers. There's one paper which was based on Greenland and so the Isua Greenstone belt, supercrustal belt, I think it is off the top of my head. And that was all about looking at carbonaceous deposits in apatite grains. And then there was one which pushed it even further back. So the oldest so far signs of life, which was in Canada, and that was looking at the hematite tubes and the like, right? Thinking about hydrothermal vents. So the answer was B, right? So they were looking at the carbon isotopes or the isotope ratio. In the later one, they were looking at that too, but they were mostly focused on those hematite tubes and casts, right? So the two bits of information that you needed were this one, time, right? And so the other one was from that to like 4.2 billion years ago, and the location as well, right? And so the older one was in Canada, this one was in Greenland, right? So just kind of recall in the sense, right? Differentiating between those two. Okay, so that's the midterm gone through. I will be preparing, so my list today are Jupiter and probably barophiles actually, because that's deep sea, high pressure, sulfur, high temperature, that sort of stuff. So I'll be preparing those this afternoon. I'll get those posted so you have time to look over them before our doing this again on Wednesday. And also I'll basically figure out a schedule for the stuff for the rest of the semester. Kind of simplifying it less into what's going to happen on days, but more into what we're going to do, right, in terms of subjects. Still don't know what's happening about exams because no one's told me yet. So we have a couple of options that have been floated, but I haven't really heard anything more than that. I have asked my boss to see if he can give me some more information. Pardon me. Most likely the quizzes I'll turn into some kind of blackboard test, I think would be most the simplest way. I've been thinking about that. I haven't actually figured out how to do that yet, but that's kind of the plan. So yeah, that's pretty much it. Does anybody have any questions? Speak now or forever hold your peace, or at least until Wednesday. Fire away, Kiara. You can actually unmute your thing and ask it. You don't have to type it out. Unless you want to type it out. It's totally up to you.
Can you hear me?
Yeah, I can.
Ah! Okay. It's actually a comment. So like Dr. Valdez usually puts quizzes online. So I was just like, you could ask him because he might know how to do it.
Sure. Yes. I mean, I haven't actually done it myself. I've used what other people have done, so I've got a rough idea. Hang on, Louise. I'll get to your question in a second. It's more what kind of questions to ask, essentially, right? Because obviously, if you're doing it at home, it's going to be open book. So it needs to be rigorous enough to actually test what you know, not your ability to look through your notes, if you see what I mean. So yeah, but I'll be asking around some of my my colleagues to see how they approach that. That's a good tip. Louise, yes, is the answer to that. So the idea is that, so these essentially are going to be what now are going to be flipped classrooms, right? So I'm going to be posting up the PowerPoints and audio recordings to go with the PowerPoints. So you can basically look through the material and do your learning on your own time, you know, however that suits. And then these sessions will be more, not really office hours, but more an opportunity to go through whatever bits of that lesson or those lessons you didn't get or you didn't understand or you need clarification on. Yeah, kind of like that, but less so for the whole period of instruction and more for, you know, more or less each thing's in turn, right? So the aim is to post up lectures and audio recordings to go with them, lectures being PowerPoints, and to do that at least I want to get about 2 days ahead of schedule, essentially, right? Going off the old schedule, so that I have all of the material up and posted, ideally a week before the end of the semester, to give people time to percolate through it, I guess, or, you know, before the next quiz or whatever, right? So essentially to get ahead of the game so that you have enough time to go through things and then ask me questions about it. I think that would be most productive. I can also keep, as I did today, I'll be able to bring up PowerPoints and go to particular things, which also leads me nicely to your next question. So that's also something I've been thinking about. I'm going to reorganize the Blackboard content folder and not do it by week, because that doesn't really make any sense anymore, because we're out of sync anyway, and it just doesn't really seem to fit very well. So I'm going to reorganize that by subject, right? So basically what we're going to be in now is extraterrestrial environments and the matching ones on Earth, right? That's essentially what we're in now. That will be the half of the remaining stuff. So that's all going to go into a folder that looks like that. And then the other half will be exoplanets and detection and so on and so forth. Right. So I'm just going to reorganize that side of things so it fits better with what we're doing now. Cool. You're welcome. Any other questions? If you do, if any occur to you between now and Wednesday, just write them down or store them in part of your mind that doesn't get erased every night, and just ask them then. Awesome. All right. Thanks very much, everybody. That was a lot of fun. I shall see you on Wednesday. I'm still available by email. So if you want to ask me stuff by email, just shoot me an email and I'm happy to answer that. If not, I'll see you Wednesday at 9. Have a great day, everybody. And hang on, let me make sure I record this. There we go. There we are. Okay, how do we do this?